Hey everybody, so today what we're talking about is gas stoichiometry. And it's just like regular stoichiometry, except instead of giving grams, going to grams, you'll probably get liters and you're going to liters. So all we're doing is dividing by 22.4 to get that liters to moles, and then we'll do a mole ratio. The big thing to know is that when do we do gas stoichiometry? Okay, we'll do gas stoichiometry when it's asking us to go from one compound to another. So if it's saying we start with like 3 liters of hydrogen gas, we gotta, and it's saying go to CO2 gas, we know that if we're going from one compound to another, we gotta be doing stoichiometry. Sometimes it's just straight up stoichiometry. Sometimes at the end of that stoichiometry problem, it'll ask us to plug into PV equals nRT. So today we're going to do a couple examples of gas stoichiometry. The process should be review, but a little bit of what to look for is what we're trying to do today. Alright everybody, here's our first problem. So how many liters of ammonia can be produced when 12 liters of hydrogen react with an excess of nitrogen? So all we're doing here is we're going from liters of hydrogen to liters of ammonia. We got a chemical equation here. Let's make sure that's balanced first. It's not, okay? We got 2 nitrogens here. Let's put 2 there to get 2 nitrogens, but now we got 6 hydrogens. So let's go ahead and put 3 in front of that hydrogen gas there. So all we're doing now is going from 12 liters of hydrogen to liters of ammonia. And here's the nice thing, right? If you wanted to go to moles, you divide by 22.4. And then we do the mole ratio, and then we'd have moles of ammonia. Well, then you gotta multiply by 22.4, essentially canceling out your first step. So a shortcut, if you guys don't want to divide by 22.4, if you're just going from liters to liters, all you could do is a mole ratio, and that's fine, okay? It'll give you the correct answer. Let's go through the long process, and then let's do the short process so you can see what I'm talking about. So first things first, we're just going from liters of hydrogen to liters of NH3. Sometimes it'll say at STP, sometimes it won't say at STP, okay? We're assuming that these are at the same pressure and temperature, and plus we have no other thing to do but stoichiometry. So let's start out with dividing by 22.4 liters per mole to get to moles of hydrogen. So we're going to take 12 divided by 22.4 to get 0.536 moles of H2. Now we got to get to moles of ammonia, which mole ratio time. So it would be a 2 to 3 ratio. So let's go ahead and multiply 0.536 times 2 divided by 3. H2 cancels out. We're left with moles of NH3, which is 0.357 moles of NH3. But we're not done yet. We got to get back to liters. So to go from moles to liters, we multiply by 22.4. So we multiply by 22.4 liters, and we should get 8 liters of ammonia, or NH3. So that was the long version where you just divide by 22.4 at the beginning and multiply by 22.4 at the end. But again, we don't have to do that because we could just do a mole ratio if we're going from liters to liters, because this step at the beginning where we divide by 22.4 gets canceled out by the later step of multiplying by 22.4. So let's just do this the quicker way, which we have 12 liters of H2. I know that I'm just going from liters of H2 to liters of ammonia, so I know I could just go straight to the mole ratio, which is 2 to 3. 12 times 2 is 24, divided by 3 is 8. So I would have 8 liters of NH3. So if you are in a situation where you're just going from liters of one gas to liters of another gas, you could just go straight to the mole ratio. No need to divide by 22.4 or multiply by 22.4, because you'll just get the same answer. If you want to keep going through that process, that's totally fine, of dividing by 22.4, multiplying by 22.4. Just know you don't have to. Alright, so here we have another problem. We don't know if it's gas stoichiometry or not, but let's see what it says, okay? How many liters of O2 gas at STP can be collected from complete decomposition of 50 grams of potassium chlorate? So I'm looking at this problem. It gives me 50 grams of potassium chlorate, one compound, and it wants me to go to liters of oxygen gas. I'm going from one compound to another. This looks like I'm going to have to be doing some stoichiometry here. Here's the thing. We're not going from liters to liters anymore. We're going from grams of potassium chlorate to liters of oxygen gas. So we are going to have to divide by molar mass and then multiply by 22.4 at the end. We can't just do a simple mole ratio because we're not going from liters to liters like we did in our previous problem. So let's get started. Let's start with what we're given. We're given 50 grams of potassium chlorate, okay? So we got to get that to moles so we could do a nice mole ratio. So let's divide by the molar mass of potassium chlorate. I add potassium's molar mass, chlorine's molar mass, and 3 oxygen's molar masses to get 122.55 grams per mole, okay? So I'm going to go ahead and take 50 divided by 122.55, and I should get 0.408 moles of potassium chlorate, okay? But I don't want potassium chlorate, I want oxygen. I'm going from grams of potassium chlorate to liters of oxygen. So in order to do that, we gotta make that bridge, which is our mole ratio. KClO3 on the bottom, so they cancel out. What we want on top, which is oxygen gas. That is a 3:2 ratio. Let's go ahead and times 0.408 times 3 divided by 2. KClO3 cancels out, so I know I'm on the right track. I got 0.612 moles of O2. Okay. Well, I don't want moles of O2. I want liters of O2. Luckily, it's at STP, so all I need to do is multiply by 22.4. I know for every 1 mole of gas I have at STP, it's 22.4 liters. I don't have 1 mole, I have 0.612 moles. But I know that if I take that 0.612 moles and multiply it by 22.4 liters for every 1 mole at STP, I should get 13.7 liters of oxygen gas. There is a decimal there. Okay? So that is a situation and where we can't just do a mole ratio because we're not going from liters to liters. We're going from grams to liters, so we have to do a mole ratio there. Here is one more problem for us, everybody. And this is how many liters of oxygen gas do you need to produce 50 liters of H2O at 3 atm and 273 degrees Kelvin. And here our equation is H2 plus O2 equals H2O. And let's go ahead and balance that. And what we're doing here is it wants liters of oxygen gas when we produce, if we produce 50 liters of H2O at 3 atm and 273 degrees Kelvin. Here, they give us some information about H2O and they want us to have liters of oxygen gas. So we're going to be doing some sort of stoichiometry here. Okay? Well, what do they give us? They give us 50 liters of H2O, 3 atm, and 273 degrees Kelvin. So you might be thinking, hey, let me take that 50 liters and divide it by 22.4. The problem is, we are not at STP. STP is 1 atm, 273 degrees Kelvin. We're not at 1 atm, right? We are at 3 atm. So we have a different pressure, we have a different temperature, and we have a volume. Okay, we have pressure, temperature, volume, and I need to figure out another way to get from H2O to O2. I can't use STP, so somehow I have to use something else. Well, luckily, we have an equation that helps us relate volume, pressure, temperature, and moles. If we could figure out the moles, we could do a mole ratio, and then we could go ahead and get to oxygen gas, liters of oxygen gas. So let's go ahead and let's do that. So let's go ahead and do what we know best, Pivnert. Right? Through Pivnert, I could go ahead and I could find moles of water, and then after that I could go ahead and do a mole ratio, and I could figure this whole thing out. Okay? So let's go ahead and let's plug in what we know. We know we have 3 ATM. We know we have 50 liters. We don't know our moles, that's what we're looking for. Our R is 0.08206, and our temperature was 273. So let's go ahead and let's solve for moles by getting moles by itself. We take 3 times 50 divided by 0.08206 times 273. Okay, so when we divide by our R and our temperature on both sides, we should get 6.7 moles of H2. But again, I don't want moles of H2, I want moles of oxygen gas. So we better be doing a ratio here. So 2 to 1. Right, H2O on bottom, O2 on top. It is a 2 to 1 ratio. So 6.7 divided by 2 will give me 3.35 moles of oxygen gas. And again, you might say, okay, we want liters of oxygen gas. Can I do STP times by 22.4? Nope. We got to use PivNert again, okay? Again, we're not at STP, so we have to use PV equals nRT. So let's go ahead and just plug it in right above that moles of oxygen. We're still at 3 ATM. Our volume is what we're looking for, but this time our moles is 3.35. Our R is always the same, 0.08206, and our temp is 273. I'm sorry, I ran out of room there. Let's fix that. Boom. Okay. Divide by 3 on both sides to get our new volume. Let's go ahead and let's do that. 3.35 times 0.08206. 0.08206 times 273 divided by 3 is 25. Wait a second here. So our volume is 25 liters, right? What could we have done instead of doing all that PV equals nRT stuff? Mole ratio, right? We went from liters to liters. The pressure and volume stayed the same. It didn't change. So what's the point of doing PV equals nRT, right? We divided by RT here, and then we multiplied by RT here. So we just kind of canceled out our previous steps. So over here, right, I start out with 50 liters of H2O. If I did the mole ratio right at the beginning, I could have saved me a lot of time and just did the mole ratio, okay? So be aware of that. If you are in a situation where the pressure and volume are staying the same, no need to do all that PV and RT stuff. You could just go ahead and do the mole ratio, because in this instance, we were going from liters to liters. The last thing with gases is Dalton's law of partial pressure. Okay, you're not usually going to have just a pure mixture of gases. You're going to have, or you're not just going to have one gas, okay? You're going to have a mixture of gases. So what we're doing with this is that we're seeing how much pressure is given off by each gas. The more molecules there are of a gas, the more it'll bounce on the inside of that container and create pressure, okay? Things that, if you have more molecules, say you have twice as many molecules as H2 than O2 in a container, that H2 is going to create twice as much pressure. Okay, it's not dependent on size because we're dealing with ideal gases here. It's just dependent on how many molecules or moles there are. So what we're doing is we're just pretty much doing a ratio. But what Dalton's law partial pressure states is that the pressure total, or the P tote, is equal to the pressure of, or the partial pressure of all the other gases. Okay, so once again, you just got to be able to do ratios. So let's go ahead and start our first problem. Alright, so in this example, if we have 3 moles of O2 and 2 moles of H2, how much pressure does oxygen account for if the total pressure is 10 atm? Alright, so all this is that we got to look at how much oxygen makes up of the total moles, and it should make up that same ratio of the total pressure. So what I like to do is I like to put moles of O2 over mole total, and then I'll put the pressure of O2 over the pressure total. Okay? Again, this is all just a ratio. Oxygen should make up the same ratio of moles as it does the pressure. Okay? So let's go ahead and plug in what I know. I know that oxygen makes up 3 moles of the total 5 moles, right? If we add the oxygen and hydrogen together, that gives us 5 moles. So oxygen makes up 3/5 of the moles. It should make up 3/5 of the pressure. Okay? So if we set that equal to our pressure, we don't know what partial pressure oxygen makes up yet, but we do know that the total pressure is 10. So if it makes up 3/5 of the moles, once again, it should make up 3/5 of the total pressure. So here you could just do a little bit of cross multiplying, or you know that 3/5 is 60%. Well, 60% of 10 is 6. Okay? So oxygen should make up 6 of the total pressure. Again, if you don't want to do that or are still lost and can't figure out the percentages, you could just do cross multiply and figure it out that way, right? 3 times 10 is 30. 5 times x is 5x. X is going to equal 6 ATM, like I just stated before. Okay? So that's all this is. They love to throw problems at you where they give you mixtures of gases. Well, just remember that what they make up in pressure is equitable to what they make up in moles. So here's another problem that you might see. We have a bowl containing 3 gases that is shown below. So we got this weird gas container separated by 3 gases, 3 moles of O2, 4 moles of H2, and 5 moles of N2. And the total pressure is 23 ATM, so that's a lot of pressure inside that. What is the partial pressure of all those gases? What is the partial pressure of O2 making up, H2 making up, and N2 making up? Again, all this is a ratio between the moles and the pressure. We know the total moles, we know the total pressure, we know the partial moles, we can figure out the partial pressures. So let's go ahead and do that. Say we want to figure out the partial pressure of oxygen. We know that oxygen makes up 3 of the total moles, which if we added up all those total moles is 12. So it makes up 3/12 of the total moles. It should make up 3/12 of the total pressure, but unfortunately we aren't dealing with 12. Here we're dealing with 23. So total moles, total pressure on bottom, partial moles of oxygen, partial pressure on top. We go ahead and we cross multiply, right? We take 3 times 12, 12 times x. You should get 69 divided by, or 69 equals 12x. We divide by 12 on each side, so 69 divided by 12 is 5.75. So oxygen makes up 5.75 pressure of that bulb. Let's go ahead and do the same thing for hydrogen. It makes up 4/12 of the moles. It should make up 4/12 of the pressure, right? But again, our total pressure is 23, not 12. We cross multiply, so we should get 4692 over equals 12x, right? 4 times 23 is 92. 12 times x is 12x. 92 divided by 12 is 7.67. ATM, and we were dealing with hydrogen there. That makes sense. We had more moles of hydrogen, so it should make up more of the pressure than O2. Last one, let's go over here for this. Nitrogen makes up 5/12 of the moles. It should make up 5/12 of the pressure. 5 times 23 is 115. 12 times x is 12x. 115 divided by 12 equals 9.58. Are pretty dang close. ATM of N2. And that's how we find the partial pressures of all those gases. And then when we add up these partial pressures, they should be pretty close to equaling 23 based on how we round it. So that is Dalton's law of partial pressures. Last thing, I just want to talk about some conceptual things relating temperature, pressure, and volume. So we need to be able to explain if temperature increases, what's going to happen to a pressure in a certain container. If temperature decreases, what's going to happen to pressure in a certain container. And you got to be thinking, what are we dealing with? Are we dealing with a hard container like a paint can or just an enclosed steel box? Are we talking about containers that can move or change volumes, things like balloons or your tires? Let's start with just fixed containers for right now. So say we just have a steel box. Steel box, that volume is fixed. That volume isn't going to change. Okay? The only thing that can really change inside that box is the temperature and the pressure. Say we have some air molecules and we increase the temperature. What is going to happen to those molecules if I increase the temperature, right? I'm putting energy into those gas molecules. They're going to be moving fast. Okay? When they move fast, they're colliding with things, okay? They're colliding with themselves and they're colliding with the inside of that container. And it's good to note that pressure increases because those molecules bump into the inside of the container. When they bounce into each other, that's not increasing pressure. It's when they hit the edges of these containers and push a force outward. So, as you can imagine, like if you were to throw a paint can in a fire, which is not something I've ever done, but if you did, that pressure would build inside that paint can because that container is fixed, and eventually it would explode. Okay, that is because when that temperature increases, those molecules inside that container are hitting the outside walls a lot more, and you're getting a nice increase in pressure. So this is when volume is constant. We're not changing the volume at all, it's just changing nice and consistent. Now let's say if we were talking about a fixed, or not a fixed container, a variable volume container, such as a balloon. So say we got a balloon and it's got your air molecules in there, okay? A balloon is just in equilibrium with the pressure of the atmosphere, right? If you got it tied off, you are going to not see that balloon increase or decrease in pressure, right? The pressure of the atmosphere and the pressure inside the balloon are in equilibrium. If the pressure was greater, that balloon would shrink. If the pressure was less, you'd see that balloon expand. If we went ahead and brought a balloon into space where there is no atmosphere, those molecules would be able to push on the inside of that balloon and expand that balloon, and eventually it would explode. So here on Earth, and we have an elastic container, they're in equilibrium. But say we increase the temperature on that balloon. Say we add some fire to it without popping the balloon, obviously. What again is going to happen to those molecules? They're going to speed up. They're going to hit the inside of that container. And that volume is going to expand. Right? Now here, the pressure is constant. But when the temperature increases, the volume is going to increase. You guys might have experienced this recently with your car tires. Okay, my low pressure tire pressure light just came on the other day because it's getting colder. Those molecules are shrinking down, they're slowing down, they're not hitting the edge of my tire as much, so my tire is getting flatter. But then once I get on the road, right, I'm getting a little friction between my tires and the road. Those molecules are getting some heat, they're getting a lot faster. They start to expand on the edge of that tire, and then my low tire pressure light turns off. So be aware of these things in terms of ideal gases. Let's talk about real gases for just a tiny moment, okay? Remember, let's go back to a fixed container. Remember that real gases actually interact with one another. They don't just bounce off each other automatically and then move at the same speed, okay? Real gases, when they are moving about, sometimes stick together, okay? Sometimes those gases bounce and they stick together and they'll fall down to the bottom of the container and condense, okay, into a nice liquid. Well, if some of those containers are condensing at the bottom, some of those compounds are condensing at the bottom of the container, are they going to be bouncing off the walls anymore? No, they're not going to be creating as much pressure. So what you tend to see with real gases is you tend to see a smaller pressure than you would with real gases. Real gases don't stick together, right? They bounce off the inside of the container. They don't stick whatsoever. They're creating a lot of pressure. Real gases do stick together. They do condense. They do fall to the bottom of the container and not create as much pressure. So be aware of that when you're thinking conceptually, when I ask you questions about how pressure would change in certain situations. Okay? Have yourselves a great day.